Hello and welcome to seminar number 22. Today we are going to talk about the liquid extraction method. And I just wanted to give you a quick overview on two applications of the liquid extraction. One is the Purex process and one is the Protactinium extraction. And let's get started. The Purex process is a method to recycle mostly spent nuclear fuel. However, you can use the Purex process to recycle spent uranium compounds in a uranium lab, for example. And the name comes from plutonium-uranium recovery by extraction. Let's say, for example, you start off with 3.3% enriched uranium-235 and 96.7% uranium-238. And after burn-up, you still have 0.9% uranium-235 left. So it's a 70% burn-up of all of the uranium, which is still enriched uranium. And then you also bred 0.5% plutonium-239 from the uranium-238. And you have some other things like 0.1% of other actinides and 3.2% of all the fission products. So you could still use this uranium and plutonium in another fuel cycle, and you want to separate this from the fission products. You can't do this by hand because burned nuclear fuel is just so highly radioactive that everything is automatic and behind very heavily shielded lead glass. But since it's also automated, you want to simplify the whole process as much as possible to prevent any possible errors. So you have your fuel rods, which are chopped by a big hydraulic shear, and they are dropped into hot concentrated nitric acid. Of course, in hot concentrated nitric acid, pretty much everything dissolves, and it's then mixed with a mixture of 30% TBP, tri-N-butyl phosphate, and 70% kerosene, which is just an unpolar solvent. You could have used any other unpolar solvent, but kerosene is on a large scale pretty much the cheapest one. This is why you used it, but you can also use hexane, cyclohexane, and whatnot. And then you have this intensive mixing, and after letting this whole thing separate out, you now have the uranium and the plutonium complex by the TBP in the unpolar phase, which will separate since it's unpolar and the hot concentrated nitric acid is aqueous. They will separate out, and then you can separate them and then focus on the back extraction of the uranium and the plutonium from the TBP complex. So you have your nuclear fuel, for example. It's all in the TBP phase, and you've separated successfully all the fission products, and then you want to get the plutonium separately and the uranium separately. You then do another liquid extraction to get the plutonium-3 nitrate, which you would oxidize into the plutonium-4 nitrate. And then you do an oxalate precipitate to form the plutonium oxalate solid hexahydrate. And then you heat the oxalate, and if you heat an oxalate, it will just decompose into carbon dioxide, leaving pretty much pure plutonium dioxide, which you could then use in a mixed oxide fuel. Same with the uranium. You can then extract back from the TBP phase with nitric acid to have then a aqueous solution of uranyl nitrate. And then if you heat a heavy metal nitrate, for example, in this case at 400 degrees C, it will decompose into nitrogen dioxide eventually and leaving behind uranium trioxide. So this is the oxides of the plutonium and the uranium, which you have now successfully separated not only from the fission products, but also from themselves. But why does all of this work? The premise is that a non-polar solvent and a polar solvent, they do not mix that well. You have your extraction molecule that isn't soluble in the polar solvent, but still has a polar group, which could bind to whatever you like to extract. So you have the TBP, then you have your polar solvent molecule part, which could then complex the uranyl or the plutonium. And since it's mostly non-polar and you have a non-polar solvent like kerosene, for example, the kerosene will dissolve the TBP, and the TBP has now complexed the uranyl while mixing. They can attract each other, and now you have the uranyl complexed, and this will then be pulled into the unpolar phase, in this case the kerosene phase, and then can be separated out. And of course it only works if your extraction molecule could only extract what you want and nothing else from the aqueous solution. So by shaking, the dissolved ions can be in contact with the TBP, can be complexed, and then pulled into the other phase to then separate away. If you are taking a closer look at the Purex process, you might want to wonder, okay, how does the uranium and plutonium look like in the solution? You have uranium as a uranyl ion, so 2 oxygen atoms coordinated to the uranium because a naked uranium atom, so a hypothetical uranium 6+, is too highly charged and would react with water, creating protons and pulling away some oxygens to form the uranyl ion. You can see that by the fact that uranium hexafluoride, which has pretty much a naked uranium 6 atom in it, reacts quite exothermic when it comes in contact with water to form this very stable uranyl ion. For plutonium, it's just a naked plutonium 4 ion. It's the most stable oxidation state for plutonium, but of course there will be some water molecules and stuff like that coordinated to it, but it's for all simple purposes just a naked plutonium 4+ ion. So if we take a closer look at the complexation of this uranyl ion by the TBP, you can see that we have water with uranyl and the saturated uranium TBP phase, and these are 2 very yellowish color because the uranyl ion produces a yellow color impression. And if we can see, after separating the water with the uranyl and adding more fresh water to it and shaking again, after like doing that 6 to 7 times, the water after a while will be very clear because you always add more water and then separate out the newly formed water with the uranyl solution. And also the TBP phase gets a bit less colored because you are constantly extracting the uranyl out of this TBP phase with water, and then you're separating the uranyl water away and adding more fresh water, and therefore diluting the uranyl concentration in the TBP phase. This is somewhat how the complex looks like. Of course, this is not the tri-N-butyl, but the tri-I-butyl phosphate. So you can see the oxygen here, the oxygen there, this is the uranium. So there is the uranyl ion, we have 2 nitrate ions, and then we have the oxygen of the phosphate group of the TBP molecule. And if you want to get some more animated stuff, I have uploaded a YouTube video here, and you can also take a closer look at the different lovely plutonium oxidation states. I think this is the video about the extraction of plutonium. Another application of the liquid extraction is the extraction of protactinium. For example, there has been a paper in the 60s where they extracted large scale protactinium-231 from spent nuclear fuel via this process, and they used as extraction molecule the MIBK or the diABK to pull the protactinium out of the solution. This, on a very small scale, is a very typical experiment in nuclear chemistry. It's the protactinium-234M generator, and you use HCl as an aqueous solution, you use MIBK in hexane as the extraction, and then the freshly formed protactinium-234M is complexed by the MIBK, is pulled into the hexane phase, which is less dense than water, and is therefore pulled towards the detector, which is up here, and then can be measured. Since protactinium-234M has such a short half-life, you can really see its decay and determine the half-life of this isotope, which is a really neat experiment for schools, in my opinion. However, if you look up protactinium chemistry, you will see that protactinium loves hydrolysis, so it forms in water very water insoluble hydroxide or oxide hydrates, and the protactinium 5+ is only stable in acidic medium because the acid prevents this hydrolysis of oxide and hydroxide, and depending on the acid that you use, it might form negative complexes, might be stable as a free protactinium 5+ ion in perchloric acid, but it also likes to form colloids, so the aqueous chemistry of protactinium is really complicated and there hasn't been enough research, in my opinion. If you look at large scales, you will see that protactinium oxide, so the Pa2O5, is only soluble in hot concentrated hydrofluoric acid, which is true for protactinium on larger scales, like in the milligram or microgram region. But in our experiment, protactinium-234M is such in low quantities, since we are pretty much extracting like 10 kilobecquerels of protactinium-241M. This neglects all of this solubility stuff because it's in such low concentration that you don't have to pay attention to the solubility of protactinium because it's such in low quantities. Therefore, it will be still soluble in hydrochloric acid, even though Litsch just says that it's only soluble in hot concentrated hydrofluoric acid. Very complicated topic indeed, and with that being said, thank you for attention and goodbye.